Hey folks, I've had a few requests for a review of the review packet in video form, so that's what we're going to do tonight. In our first question, we are given a nice little function, p of h, with a starting value and an exponential term that represents a bacteria population. And they've even graphed it for us, which was very kind. And our first task is to use that graph to figure out when the population will reach 100,000. Well, that's not too bad. We can look at our y-axis where we have our population in thousands, find that 100,000 line, trace it out to see where it intersects with our function. So that's going to be where in time our function gives us 100,000 bacteria. And we can trace that down and see about where that intersects with our x-axis, or what our x value would be at that point. And that looks to me like it's pretty close to 4.25 from this graph. It's difficult to be much more precise than that. But the good news is we have the function and we have the values, so we could solve for a precise answer at this point. Right? And that's exactly what we're going to do. So part B is worded in a slightly confusing way. Right? It wants us to say y log base 2 of 20 is going to give us that same answer, that close to 4.25 value in this function. And the cleanest way to show why that expression is equivalent to RH, right? The hours that pass when we reach 100,000 bacteria, is to plug into our exponential function and solve, right? So I'm going to set P of H equal to 100,000. And I know that equals my starting value, 5,000 times 2 to the H. And if I can solve for H, right, I should be able to find log base 2 of 20, and it should be close to my original H that I found here. So first step, divide both sides by 5,000. Which gives me 20 is 2 to the H. I then use my definition of logarithms to rewrite this in logarithm form. I'm going to take a log with a base 2 of 20, and that's going to give me H. Oh, hey, that is exactly what I was hoping to find. So if I want to give a narrative explanation of why this works, I could say, just describe exactly, right, what I did. I could say when I plug in 100,000 for my final population of bacteria, I find that log base 2 of 20 hours have passed. Another way that we can think about it, another way that we could describe it, is we know that an exponential function and a logarithm of the same base are inverses of one another, right? So in this particular case, we're looking for what I plug in on one side for my x to get my 100,000 on my y. But we'll talk more about inverses and exponentials and logs later in this packet. Okay, let's take a look at 2. So 2 is one of our most requested review problems. So hopefully by the time you're watching this video, we've done this problem together, but this way you'll have a record for how it works that you can watch multiple times if you so desire. Right? And we are given a function for the population growth in the United States between 1800 and 1850, so that's when they tracked it, but we'll be able to use this function to extrapolate on either side if we want to. Um, and we know that it's in millions, so that's going to be helpful to us for keeping our scale in order. First question, not too bad. What was the population in 1800? We can read that right from our equation, right? So I would like to note, right, that our initial value, right, always lives right here before our base and our exponent. And this is a continuous growth situation. We notice that because we have e as the base of our exponent, right? So our starting value, which is defined as what the population in 1800, is that 5. And this is in millions. So our final answer is going to be, whoops, 5 million people. Okay, so this is a fun adventure. We then want to graph this equation, this function, and we can use a tool like Desmos, and we're going to have to adjust our particular window to its specifications to be able to actually see what's going on with this graph. So I am going to try and see if I can take us there right now, and there may be a cut in this video if I get turned around. Okay. I'm going to go to Desmos, graphing calculator. Okay, and since I am not, oh, will it let me log in? Yeah, I'm definitely going to have to cut this out of this video, but that's okay. Nope. Okay, so we are in Desmos and we have this function graphed, and we have set our uh, window to their specifications. To see how to do that, we can tap the wrench, and you can see at the x-axis and y-axis, I've moved it a little, but we're between about 0 and about 100 on the x-axis and about 0 and 40 on the y-axis, and that lets us see cleanly what our point of intersection is here, right? And if we highlight it, we can grab that point and see that on our function, when y is equal to 20, our x is equal to 49.5 or thereabouts. So we're going to take that point of intersection that we got from our graphing tool, and we're going to head back to our worksheet. Okay, so we discovered that we could do this. We found the point of intersection at 49.5 or thereabout 20. Now let's think about what that means. So when y equals 20, right, that's going to be some population value. It's going to be in millions as well. So we'll say that the population of the US was 20 million. And when? Well, that's going to correspond with our x value for that point. So 49.5 years after this function started measuring our population growth. So 49.5 years after 1800, or roughly in 1849, maybe about June. Okay. Next, number 3. We get another bacteria situation, another nice little P of H, population by hours function. And for each of these questions, we're going to show as much work as we can to show how we know. Okay. First question is, how long does it take the population to double? Well, our starting value is 1,000. So when we double, our value will be 2,000. So we can say, how long does it take our population to get to 2,000? By setting P of H equal to 2,000 and solving the equation that we get, 0.4H. Okay. Again, our first step, get rid of that 1,000. So we want to know, when is 2 equal to e to the 0.4h? Right? And again, we want to use our logarithms, and this time we're operating with a base of e. So that's how we know to use ln, right? Because the natural log is the log with a base of e, just ln. Okay. So we can write this in logarithmic form. The natural log of 2 is 0.4h. And we can solve that. I'm going to pop back over to our calculator to get us that value really quick, and we'll probably cut this part of the video too. Okay, so that ln of 2 divided by 0.4 comes out to about 1.7328, or about an hour 45. Hour 45 minutes. And that makes sense, close to 2 hours when I have continuous compounding of a 40% growth rate. And we can see that 40% growth rate in our initial equation. Highlight a different color. That 0.04, that's our R, right? Represents a 40% growth rate. So this is growing pretty fast, so it's not surprising that it wouldn't take too long to double. Okay. Next question, super similar. How long does it take the population to reach 100,000? Well, just like before, we can set P of H equal to, that's not even 100,000, that's a million. Whew, getting late here. And again, our first step is to divide by 1,000. Which leaves us with 1,000 equals e to the 0.4h. Again, we can take the natural log, ln of 1,000 equals 0.4h. Divide both sides by 0.4. And I want to note that if we're in a pinch where we don't have a calculator, or in a non-calculator part of a test, or any circumstance where we just need to like get this down and don't necessarily want to solve it all the way out, right here, this h equals ln of 1,000 over 0.4 is pretty simplified form. And it's as precise as we're ever going to be, because as soon as we plug this into a calculator and get a decimal, it's going to be less precise. We're going to have to do some rounding. So the longer I can keep it like this on a test and use this for computation until I absolutely have to get a final number, the better. But just for today, let's plug that into a calculator and see where we end up. Looks like about 17 hours and 15 minutes. Or 17.26 hours. Circle that so we have it. Circle this so we have it. So problems like this are not bad. They're pretty much plug in, use what we know about natural logs to solve the equation for a set value that's in our exponent. It's going to get more exciting. Okay, so here we have a series of problems that we should be able to do without a calculator. If we're just plugging this in into a calculator, we're going to run into some trouble, right? Because the base in each of these problems is what's unknown. And if it's hard to see right from this log form what the answer to each of these problems might be, and it is for me, I suggest writing in exponential form first and seeing if it's easier to see. So to do that, I have my base of b. I am taking it to the second power, and I know that that's going to be equal to 144. Right, so that's just applying my definition of logarithms. My base becomes the base of my exponent. On the other side of my equal sign, I find my exponent, and the 144 pops over to the other side of the equation. Right, so what squared is 144? 12. Cool. Do the same thing here. B squared equals 64 to get it into that exponential form. I want to know what squared is 64. That sounds like 8. I'll say B equals. Right. Now I want to know what cubed is 64. As I still have my base of b, but this time my exponent is a 3. And that I know is 4. I want to know what to the 6th power is 64. Noticing a pattern here, in this case my b is 2. 64 is a great number for powers of 2 and numbers related to it. My last one, a little more complicated, got a fraction kicking around in here. So here I want to know what to the negative 2 power is 1 over 9. And I want to remember that my negative exponent there, means I'm putting something into the reciprocal. So I could rewrite this as what squared is 9. And that's going to give me a b equals 3. So we are well assisted by having a pretty intuitive sense of number here, and some times table stuff, and just like comfort with 2 to powers and 4 to powers. If you run into a little snafu there, you can certainly, I think this is probably part C, is where it starts to go a little haywire. We know it's got to be something that's less than 8, and we know that factors of 64 include things like 8s and 4s and 2s, so we could have a good sense that we might want to try a 4 if we didn't have a calculator handy. And if we're taking b to the 6th power and getting 64, we know it has to be pretty small. So 2 would be a pretty intuitive place to try, and 2s are easy because we're just doubling. Powers of 2 are not bad. So those are my strategies for approaching this without a calculator. Obviously, we could take the 6th root of 64, take the cube root of 64 with a calculator if we had that available to us. So similar question about estimating in number 5, and I had some specific questions about this one as well from your exit ticket, so hopefully this will be useful to you as we move forward. Okay, so these guys as well, I don't necessarily have the cleanest idea of what they are. I know these two. All right, so I'm going to do the easy part first every time. If I don't know where to start with something and that log base 2 of 11, my whole heart is like, why? Then instead, I'm going to look at the ones that look a little more straightforward. Log base 5 of 25, that's asking me what power do I take 5 to get 25? And I know that that's 2. So I know this is 2. Whew, started. Similarly, log base 10 of 1, that's asking me what power do I take 10 to get 1? And I know that that's 0. Right? 10 to the 0 is 1. And in general, if I see a log with a base something is 1, my answer is going to be 0. So then I want to figure out where these other things all fall, right? And I'm going to take a look, right? I'm going to start with powers of 2. So this is asking me what power do I take 2 to get 5? Well, it's got to be more than 2, right? Because I know 2 squared is 4. And it's got to be less than 3 because I know that 2 cubed is 8. So I know that whatever I have to take 2 to get 5 has to be between 2 and 3, right? Because I'm concerned with the powers here, what power I'm taking 2 to. And I know it's got to be probably closer to, 2, because my 5 is much closer to 4 than 8. Right? So I'm going to say in this case, it's between 2 and 3. I'm going to use similar logic, right, for my other two cases. So here I want to know what I take 3 to get 5. That's got to be between 1 and 2, because 3 to the first is 3 and 3 squared is 9. So whatever I take 3 to get 5, 5 is between 3 and 9. So my power has to be between 1 and 2. So I'm going to write that down so I have it. X here is between 1 and 2. This value is between 1 and 2. And last but not least, I want to know what I have to take 2 to get to 11. Well, that's going to be between 3, because 2 cubed is 8, and 4, because 2 to the 4th is 16. So I know in this case, right, I'm going to write that as x is between 3 and 4. And now it's cleaner. Now I can put these in order. I know what to do. I'm going to write them in red. My log base 10 of 1, that's my smallest. My log base 3 of 5, my next smallest. Then I hit my 2, log base 5 of 25. Then log base 2 of 5. And my greatest is log base 2 of 11. So again, the trick there is to translate from the log notation that is difficult to understand to exponential notation that I can understand and estimate, right? I'm using benchmark integer powers to see where the logarithm that I'm concerned about will fall. All right. Whew. This one has less words, which may be a relief to some of you as it is to me. Just solve. Solve. We love just to solve. And we know how to solve this, right? We want to try to get our term with our exponent by itself, and then we want to use our definition of a logarithm to rewrite it. So my first step, divides both sides by 9. And then, yay, I can see that 10 to the 0.2 t is equal to 100. My math is even easy. Now, if I want to be super formal, at this point I can write, right, log base 10. I don't really have to write because my common log, when I just write log, is a base of 10. But for today, just so it's super clear, I'm going to write it. So log with a base 10 of 100 equals 0.2 t. And I know what log base 10 of 100 is because I know that when I take 10 to a power of 2, I get 100. So I know that 2 is equal to 0.2 t. I can divide both sides by 0.2. And I know t is equal to 10. If I'm not sure, this is a really easy one to plug back in, at least at this step, right? 10 times 0.2 is 2. So 10 to the 2 would be 100. Okay. Number 7, the dreaded word explain. I want to take some time to think through how we can use mathematical notation here to show some work that might make it easier to explain than like writing out a whole sentence. And this is going to be very, very similar to number 5 that we just did right here, right? Because it's asking us sort of where the natural log of 4 falls on the number line. And we just did a bunch of work estimating that sort of thing in number 5. The difference here is we're just working with e. Right? So I'm going to say, right, like, let's let the natural log of 4 equal x. I don't know what it is, but let's call it x so that I can talk about it. In that case, I know then e to the x is 4, right? Just by definition of the natural log, because the natural log is the log with a base of e. I'm going to see how many times I can say that out loud in the course of this video. All right, so what's my x here? If I want to like estimate what this x would be, and we know we have a hint for what numbers we should consider here, right? We want to think about 1 and 2. So let's think about what e to the 1 is. we know that that's like 2.71 something 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 by the limit definition of E, and just by that's what E is. Um, so then we also know that E squared is going to be 2.71, etc. squared. That's the same as, right, 2.71 times 2.71, etc. And so how do I know that that's more than 4? Right? Which I can say is greater than 4. Well, 4 is 2 times 2. And whatever this number is, it's something bigger than 2 times something that is also bigger than 2. So it's going to be more than 4, necessarily. So since E squared is greater than 2 squared, right, ln of 4 is going to be less than 2. Okay, so that shows us just, I think, maybe the tiny gap that remains, right? I know that x is going to have to be more than 1 because e to the 1 is less than e to the x, and I know that x is going to have to be less than 2 because e to the 2 is more than 4. Okay. Oh, now there's a lot of words. So for those of you who are cringing with me, we got this. I believe in us. It does have an illustration. We can get there. So 8 gives us a pair of graphs for the revenues of 2 companies. F and G, they're labeled for us in our graph. I'm going to highlight them with corresponding colors to make them a little easier to see. F is F, and G is G. So we're not given the functions specifically. We don't have any actual equations for the functions. But we do know that our revenue is measured in thousands of dollars, our time is measured in years, and we know the y coordinate of that intersection. So I'm going to write that our intersection here is at x, comma, 215.7. Just so we have that recorded. And then hopefully I don't have to read this more times. And we're going to take each of our questions one by one and see if it's true or not. Okay. So keywords that I want to pull out of this first part. Right, this tells us the revenues. The intersection of the graph tells us when the revenues of the 2 companies grow by the same factor. I'm going to give that a false, and here is why. The intersection of the graph tells us when the revenues of the 2 companies are the same, which is not the same as them growing by the same factor. Right? When they're growing by the same factor, that would be it's when they're being multiplied by the same term. But here we don't know what they're being multiplied by. We just know that they equal the same thing. They have the same y value. They have the same revenue at that point in time. Oops. And that's exactly what we know from B. So I'm going to pick B as true. Okay. At the intersection, is f of t greater than g of t? Well, no, at the intersection, we just said they're the same. They have that same y value. The functions are equal to each other at the intersection. So just like A, C is right out. And then that's what we're given in D. At the intersection, f of t is 215.7 and g of t is 215.7. In order for it to be an intersection, they must have the same value, the same x and the same y. Oh, I circled the wrong thing. Okay, and then for E, it says we need to know both expressions that define f and g to find the value of t at the intersection. Well, let's think about that. Do we need to know both functions, right, to find our x value here at this intersection? Well, if we had one, I think we could do it. Because given any y value of a function, we can find its x value. So if I knew f, I could set it equal to 215.7, solve for my exponent, use logs to do it, and that would give me my x value there. And if I knew g, I could do the same thing. I could set it equal to 215.7 and solve for my time at that point in time. So I don't need to know both in order to find my intersection point. I just need to know one if I know what I know here, which is that they intersect at a y value of 215.7. Just need one. It would be nice to have two because then we could like plug it into both and confirm. That would be really clean. But we don't necessarily get that all the time, and we don't necessarily need it in this particular case. So just to fill in, so we have it, the false, true, false, true. All right, let's take a look at the city in Texas. Population of fast-growing city in Texas can be modeled with this equation P. So I am going to highlight my equation. That's not my highlighter, my equation P. P. And a fast-growing city in Tennessee is modeled by Q. So I'm going to highlight that guy too. In both equations, we're measuring since 2016, which is good. It would be weird if it was different. And we're measuring the population in thousands. Same thing, good. It would be weird if it was different. The graphs representing the functions are here, and the point that they intersect has a y coordinate of 271.7. So we're in a similar case to our last question, where we can label this point of intersection x 271.7. So you have both functions and the point of intersection. We have so much to work with. What does the intersection mean in this situation? Well, it means where both of these equations are true, right? Like any point of intersection is where both equations are true. And in this case, in the context of our question, it's going to be the year that both cities have the same population. And if we're being really specific, we want to say the year after 2016 that the two cities have the same population. And what that population is. So at some point before or after 2016, roughly this many years, right? Both cities at the exact same time had a population of 271.7 thousand. All right. So we want to know when that was. It's hard to read from a graph, as we've established before, especially when like our axes aren't labeled as clearly as we want them to be. So we're going to do it the more precise way by solving these equations. So in our first case, we have P of t is 271.7. So we can plug that in. We can say 271.7 equals. And this is P, so it's our green equation, 82 times e to the 0.078t. So just a side note, that 0.078 says that this city is growing at a rate of 7.8%. Okay, we want to get rid of that 82 to start. And that gives us some kind of messy decimal. I'm going to keep this as a fraction as long as I possibly can, right? Forever if I possibly can. Um, I know these are going to cancel out. I know my next step is going to be to take the natural log. Um, so I'm going to be left with here the natural log of 271.7 over 82 equals 0.078 t. And then I can pop over to my calculator. And I'm going to want to use the same situation. 271.7 divided by 82. And at the end, I'm going to divide not by 0.4, but 0.078. Gives me about 15.36. T equals about 15.36. Then I do exactly the same thing for my second case, right? I'm again going to set it up 271. Draw myself a little line between them. 271.7 equals, now with my second equation, 132 times e to the 0.047 t. Same steps, divide by 132, divide by 132. And then I'm going to note that the ln of 271.7 over 132 is equal to, nope, 0.047 t. I'm going to go back to my handy calculator. Here what changes is I have 132, and my rate is 4.7%, so 0.047. And oh hey, I once again have 15.36 or thereabouts. T is about 15.36. It should be completely unsurprising that we get the same thing here, right? And if we get something different, when we just explained clearly why when our y is equal to 271.7, our x's should be the same. If we then got something different here, that would be a really good clue to check our work, right? Probably plug something into a calculator weird, who knows? But we know they should come out the same. So it's also a good check to make sure that we're doing it correctly if they come out the same. So then here's a fun question. How could we, or why can we, find out what that t-value would be by, instead of solving either of these equations, solving the equation p of t equals q of t? So by definition, at the intersection, the y values of these functions of p of t and q of t, that's q, are the same. That's what it means for it to be an intersection, right? And the y value of those functions are just p of t and q of t, right? So thus, at the intersection, at whatever t value is, that gives us that intersection, p of t will equal q of t. When we set those equal to each other, that gives us a single variable equation. We'll just have t's. That'll be our only variable, right? With the same base, e, that we can solve. So I've got a lot of things going for me. They have the same base already, so I won't have to convert it in any way, right? They're in the same universe. They have the same time variable. So if I set both of those functions equal to each other, I know it's valid because I know that my y values are the same. And that's all that p of t and q of t are. They're y values of this function. These are graphs of x or t, q of t along here, and t, p of t along here. So we could solve it. We don't have to, and we already have that t value, so I'm not gonna. And that is actually, scrolling back slightly, something that I've seen folks do sometimes, right, is if a question asks them to explain how they would do something or why something works or um, something fundamental to the problem, I see folks sometimes then go on to try to do the thing that it's discussing or just solve, right? Jump right to solving. If a question isn't asking you to solve, it's probably more trouble than it's worth to solve it. If you don't know what else to do, sometimes solving can give you some hints for how you could explain yourself. But if it doesn't ask you to do a thing, you don't make yourself crazy trying to do it. And in general, make sure that you're answering the question that's being asked of you. Not, I see lots of answers that are right answers to wrong questions, which is really easy to do. So don't make your life harder than it needs to be. Make sure that you're answering the question that is being asked. Okay, we're making progress. This is going to be a long one, guys. Where are we at? Number 10. Okay, I've got a new function f. F of x is 100 times 3 to the x. And here I'm not going to have to solve this either, right? But I am going to have to compare this function to these other 5 functions, right? And see whether they will intersect at a positive value of x. So that's a lot of pieces to keep in our head, right? But in general, in order for these functions to meet at a positive value of x, what do I need to be true, right? I need them to cross. So I need there to be some value, some positive value of x where one is greater than the other, and some positive value of the x where they've swapped, right? I can draw us a little graphy graph here. Right? I could have one function that starts here and curves like this, and another function that starts here and curves much more steeply. They would intersect. Right? But if I had a third function, a secret third thing, right, sort of starts lower than both of them and curves up slower than both of them, right? That function's not going to intersect with either, right? My green function, because it has a slower rate of growth and it starts lower. So it's just never going to have the power to catch up, right? And that's opposed to, right, two functions where one starts higher than the other, right, but grows slower or vice versa. Okay, so that's our theoretical background. We're looking for this kind of case where they overlap, one starts higher than the other, but grows slower. All right, so I'm first going to think about A. Does it start lower or higher? Well, it's going to start lower. Because its initial value is 10 when I read this function, and my initial value of the f of x in my problem is 100. So 100 times 3 to the x is going to start much higher. And then is it growing faster or slower? Well, the growth rate is going to be determined by, right, this e part of each of my equations, or 2 or 10 part, right? And is e to the x gonna be a steeper slope or a less steep slope than 3 to the x? Well, e is 2.71 something something. So it's definitely less than 3. So when I raise it to the same power, if it's a positive power, it's always going to be less, right? So it starts lower, it grows slower, it is always going to be below my function f of x. So a is out, 1 down. Now that we see the logic, right, it's not as bad to think through the rest of them. For instance, with b, is it going to start lower or higher? Well, it's going to start higher. Because my 500 is greater than my 100. But it's still growing at that e to the x growth rate, so it's still growing slower. So if I've got a function that starts higher but grows slower, that's like my blue function here, right? If red is I'm just going to label red here, my f of x, right? Then blue is an example of what b could be doing here, right? Starts higher, grows slower. So I'm keeping it. I like it, but I like it in blue. Okay, C. Just like part B, it starts higher. And then it's a little harder to see if it grows faster or slower. So I'm going to rewrite this so it has an e to the x and not an e to the negative x, because that's annoying. So if I have a negative exponent, that means take the reciprocal, right? So e to the negative x equals 1 over e to the x. And then my question is 1 over e to the x going to be a greater or smaller multiple than 3 to the x? Well, 1 over e to the x, as x gets super, super big, it's going to get super, super small. Remember when we talked about rational functions, right? I have an exponent here in my denominator. That thing's going to get huge as x approaches infinity. So the denominator is going to get huge. So this whole fraction, as x approaches infinity, this guy approaches 0. Right? Its limit as x goes to infinity is 0, if we dig back in our brains, right? Okay, so it's definitely growing slower. One could argue it's even shrinking. So it's definitely going to be another one of these cases where it starts above and ends below our f of x function. So that's in, we're keeping it. Okay. Similar logic here. 1,000 is greater than our 100, so it starts higher. And then 2 to the x is definitely going to grow slower than 3 to the x. Just on the face of it, 2 is less than 3. So they're going to cross. And in our last case, 600 is greater than 100, so it starts higher. And then 10 to the x compared to 3 to the x, the 10 is greater than our 3, so it's going to grow much faster. So this would be something compared to our f of x in our little doodle drawing. I'm going to give us another green one. This would be something like whoop. It's both steeper and it starts from a higher position. So that's out for sure. B, C, and D are in because they will cross our function. A and E are out because they're either entirely below our function f of x or entirely above our f of x on our graph of these functions. I love that problem. Lots of thinking, not a lot of like doing complicated math equations. So very, very fun. All right, making progress, making progress. Half-life of nickel. Half-life of nickel 63, special nickel, is 100 years. Someone says an artifact with nickel 63 in it will lose a quarter of that substance in 50 years. Whew. It is not immediately obvious to me whether that student is correct or incorrect. Probably not immediately obvious to you. I have my suspicions, right? Because 50 is half of 100, so they're sort of doing like a half of a half. And I know that these curves don't work like that. They're not like linear in that way. This is going to be exponential. So I'm thinking it's no, right? That's my judgment. But how could I prove it, right? Because that student is going to look at me and be like, but it makes sense to me, obviously. It's going to be a quarter, right? But I have to explain it. I have to make it make sense. So we're going to do what we always do when we have a bunch of words describing a mathematical relationship and we don't immediately understand what that mathematical relationship is. We're going to get it into math, get it into an equation. So let's write a function for this half-life, right? The amount of nickel 63 after a certain amount of time is going to be equal to whatever my initial value was, the initial amount of nickel. Calling it A for now because I love A as a starting value or leading coefficient. My B value here is that half-life, so 1/2. Excuse me. And I am taking it to my time over 100 years. So this lets me, putting that 100 in the denominator of my exponent, lets me plug in an even number of years and sort of auto-converts when I do that. Okay. So there's a function that's going to model the behavior of nickel 63. I don't know A and I don't care. I do, however, know the time that I'm concerned about. I know that that's going to be 50 years. So I'm going to plug that in for t. N of 50 then is whatever my starting amount of nickel is times 1/2 to the 50 over 100, aka A times 1/2 to the 1/2. So in order, right, for it to, so best way I think to see this, right, that 1/2 to a 1/2, right, is the same as A times the square root of 1/2. And the square root of 1/2, right, that is our actual factor that we're multiplying our A by to get our amount of nickel after 50 years, is not equal to a quarter. They're not the same. Plug it into a calculator if you so choose, right? So it doesn't matter what my initial value is, whatever the initial value is. After 50 years, we'll have the square root of 1/2 of it, or times it, not a quarter. That's not a quarter. Of it, right? So here I've shown, right, that this particular person is incorrect because I've found the actual correct value. And by finding the actual correct value, right, I've shown that it's not what they supposed it would be. Okay. Fun facts, this one's like a guess and check problem. So I think it's a really valuable one to go through, but maybe less valuable for me to explain. I can certainly explain how I would go about estimating these values, and then plugging it into the calculator is incidental, right? Log of 123, it's log base 10 of 123. My power of 10 that's closest to 100, right, or that's closest to 123 is 100. So like I can think, right, 10 squared is 100. So I know that the log of 100 is 10, right? Log of 100 or is 2. So then my estimate here for the log of 123 is going to be like greater than 2. Not a lot greater than 2, probably 2 point something something. Not a lot. Very close to 2. And I can do a similar thing with the log of 110,000, right? I can think about the log of 100,000, right? Which is 5. So my log of 110,000 is going to be more than 5. Not a lot more than 5, just a bit more than 5. It's going to be close to 5. And similarly, my log of 1.1, that's going to be really close to my log of 1, which is 0. So this is going to be just a tiny bit bigger than 0. Right? So in each case, right, I don't know the log of 123 straight up, but I know a log that's near it, right, a log of 100. And I can use that to estimate what my value will be. And then when I plug them into the calculator, just for giggles, I get 2.0899, 5.04139, and 0.04139. So feel free to bop over to a calculator, check them for yourself, pause, and continue when you are satisfied that I am not lying. All right. Here on the other side, not lying is me. So we're back to graphs of functions, right, and graphs of exponential functions. And this time, instead of comparing a couple of different functions with e in the base, we're comparing two very similar functions that have different bases, right? In our case, graph 1 and graph 2, I don't know which is which, but I know that the two functions that I care about here are f of x and g of x. We're going to try to figure out, using those same sort of ideas for comparing functions, which is which. Okay. So I can see that they both have the same starting value, and that's good news because both of my equations have the same starting value. So they're starting at 100. Right? And then graph 2 is growing faster than graph 1. Right? Graph 1 is growing slower, graph 2 is growing faster. Graph 2 has that steeper slope. Right? It's getting bigger faster. So I want to figure out between my two equations, right? Is this growth factor, this e to the 0.2x, or is this 1.2 to the x greater? So what do I know about them? Right? If I'm looking at my f of x function, right, that 1.2 in this kind of a function suggests I am growing by 20%, right? Each time I add 1 to x, right? Each time x gets bigger by 1, right, I get another 20%, another 20%, 20%. If I imagine x as years, right, then I'm growing by 20% each year. And it's easiest probably in this function to imagine it in years, even though we don't know for sure that it's annual growth, but it doesn't matter what kind of growth it is. It's just easier to give us that like benchmark in our brains. Okay. So then in our g of x, right, we also have 20% growth each time I add 1 to x, but it is compounding continuously. And I know that because that's what my e in this function does. That's what a PERT equation like this does. It always is our like indicator that we are compounding continuously. Our number in our exponent is our rate, that's our 20%, and x is how many years in this case as we're pretending the duration of our like function is, or like when we're measuring our function. Okay. So I have the same growth rate, the same initial value, But in one case, ooh, we're going to have to go fast. In one case, right, I'm compounding annually or over an interval. And in the other case, I'm compounding continuously. And when I compound continuously, as we've demonstrated when we derived the limit definition of E, I'm going to get steeper. I'm going to grow faster. So that means my graph 2, which is steeper, is going to be my compounding continuously. And my graph 1, which is shallower, is going to be compounding once or annually. So I could write that graph 2 is g of x, and graph 1 is f of x. Moving on. Oh, look, this is a graph of just e to the x. Lovely. So 2 questions. First is how we could use the graph to get a sense of what 300 equals e to the x would be. Well, this isn't too bad. I know my x's are on my x-axis, right? My y's, or my f of x's, are on my y-axis. I've just gotten a new input of a y value at 300. So I can see what my x value would be at about 300, right? We can see what the x value is when y is 300 on this function. Looks like it's going to be like 5.6 maybe, 5.7. And what if I wanted to find ln of 700? Well, I can first note, right, that I can write this in exponential form. This just means when does e to the x equal 700? Because the natural logarithm is the log with a base of e. So then I can do kind of the same thing. I can see when is my y value 700, and then what is my x value at that point. I can also skip this step if I'm feeling super clever, and I want to recognize that the natural log is also the inverse of the function e to the x, right? So that means if I have an x input into my ln function, like the 700, I can read that as a y input into the e to the x function, right? So I just say, oh, ln of 700, find 700 on my y, see where my x is. Same deal. So I can see what the x value is when y equals 700. Easy peasy. And do we need to actually estimate these? No, because we are asked how we can use the graph to estimate them. 15 here, I think a lot of folks also didn't like. So it's a great one for us to talk through here, and hopefully by the time you're watching it, we will have gone over it in class. It's one of the ones I have marked for that. So we are given more bacteria. This is like the ickiest possible problem set, just bacteria everywhere. Population in thousands, as is typical for bacteria, if not millions, and time in days. Okay, so slower growing than like hourly ones, which are really starting to upset me. Right? And since it was measured to be 1,000, so we have our starting value at 1,000, right? And it can be measured by the equation days is log base 2 of the population. Right? Whew. So I don't know about you, but I have a much easier time of understanding how these questions relate to each other if I have my equation both in log form and in exponential form. So I'm going to rewrite this equation in exponential form too, just so I've got it kicking around with me, right? So I know if log base 2 of p is d, then when I take 2 to the d, I get p. Cool. So now we can analyze using our 2 equivalent expressions and see which statements are true. It says each day the bacteria population grows by a factor of 2. Well, that's true, right? Each day right? I multiply by 2. I take 2 to that power, right? So I love it. The equation p equals 2 to the d also defines this relationship. I just said it did. That's what happened when I wrote it in exponential form, so I love that too. Does the population reach 7,000 after log base 2 to the 7,000 days? Well, let me take this expression, log base 2 to the 7,000, and see if it works out for me. So that would be 2 to the x would be 7,000. I don't think that's going to quite work, and here's why. All right, our whole function is in thousands, right? Right. So in 7,000 days, right, we're going to have way more than 7,000 bacteria. This is what happens at log base 2 of 7 days. So this guy's out because our function is already in the thousands. And that's why when we look at them, right, that initial value of 1,000 doesn't seem to appear because 1,000 in our function is represented by 1. Is d equals log base 2p a logarithmic function? It is. I also just did e out of order. So we're going back to d. Right? Does log base 2 of 10 tell us when the population reaches 10,000? Yes, because again, our populations are expressed in thousands here. So this 10 is 10,000 actual bacteria. Right? And last but not least, e. Right? It says the equation 7 equals log base 2 of 128 tells us that the population reaches 128,000 in 7 days. And I argue that that is indeed true. So our 128 is in thousands, and that's our population, right? And what we get, right, is how many days, right, is D. It's on the other side of our equation here. Population is our 128. Days is our 7. Okay, not so bad. Here's a graph of a logarithmic function. We know nothing about it except its graph. Whew, okay, okay. We want to know the base. So the first thing that I want to do here is I want to think about some points that I can recognize. And I can see, right, that I've got at least one clean point at 3 1,000. So that suggests to me, right, when my x equals 1,000, my y equals 3. I'm like, all right, that looks pretty suspicious to me, because I know in the back of my head, right, like I'm just sensing this here, that 10 cubed is 1,000. So just parenthetical, right? Maybe I have a base of 10. So I'm going to check out some other values that might tell me more. I'm going to look at what happens when x is 100, since I've got this suspicion. All right. So x is 100, so this is 2, 4, 6. Ooh, it's going to be even harder to see, right? Because this is sort of in less than that. So 100 is going to be like less than half of this guy. Oh, which does look like it's about 2. So that confirms for me that I'm looking at, right, a base of 10. Because in a logarithmic function, right, it's flipped x's and y's from my exponential function. So if I had an exponential function of 10 to the x, I would expect a bunch of x's that were like 1, 10, 2, 100, 3, 1,000, 4, 10,000, etc. And if I then want to consider like the log of x, I'm going to give us a little more space here. Instead, I want the log of x. Then my x's and y are going to flip because it's an inverse function. So when my x is 10, my y will be 1. When my x is 100, my y will be 2. When my x is 1,000, my y will be 3. And that looks a lot like what I'm seeing in this graph. So if I explain how I know, I would say that my y values are exponents I would take 10 to get my x values. So in an exponential functions, my x-axis has my exponents. In logarithmic functions, my x-axis has my outputs. They're flipped. Okay, getting there. We're closing in. We're closing in. I've got A, B, C, D, and I have 3 functions, or 4 functions, and I want to match them up. Right? So it looks like if I'm just looking at my logarithmic functions, they have different bases, and that's all that's different. And the bases are going to determine how steep each is. So I want to match up here, right, which of these are going to be steeper than others, right? And one way, like sometimes I think of it because exponentials are so much easier for me to imagine, right? You can rewrite these as exponential functions and then imagine this whole graph like on its side, right? So the ones that are like D is going to be our steepest, right? Because um, it's getting longer and longer and longer. So whichever like exponent has our like would have had the steepest graph, its logarithm is going to be the least steep, I guess is a way to think about it because they're inverses. Right? So in these 4 functions, right, I want to think about which one is the most steep as which one has the greatest base. So I'm going to consider B here because 10 is going to be the biggest base that I have here. It's bigger than 5, bigger than 2, bigger than 2.71, which is E because the natural log is the log with the base of E. Okay. And so then when I consider this like graph D, which is like the most shallow, I guess, I want to see whether it does in fact fit this 10, right, which would be steep if I had an exponential function. So I can consider like some points on this graph. Like I see that when I have an x value of 100, I should have a function value of 2, right? And when I have an x value of 1,000, I should have a function value of 3. And that 10 squared is 100, 10 cubed is 1,000, suggests that I'm correct. When I plug in 1,000 for x here, my y value is 3, and that matches this function. So I'm going to say B here goes with D. 1 down. Okay. Then the next most steep, right, is 5. Right, that's the next biggest base. So my guess right, is that C is going to go with C, but I can check it, right? I can look at some cool power like where I see I might have an intersection. We're going to see one close to 125. Yeah. So I see a point that would be 5 to the third is 125. And that's true. Right. So I'm going to label this 125, 3. Right. So when I put x equals 125 into my function, I get back 3. When I put x equals 125 into my function, I should get back 3. So C goes with C. 2 down. I'm going to keep working my way up the graph because my theory is that the greater my base, the shallower my log graph, and so far it's holding up. So the next one I'm going to look at is ln of x, because I know E is 2.71 something 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 greater than 2. Right? So this one's going to be a little harder to tell because E is a messy number. So I'm going to say tentatively, let's posit this, and then we're going to check A and make sure that it works, because I can do powers of 2 in my head in a way that I can't do powers of E in my head. All right, so I'm finding some points on my A function. And I see 2, that they're pretty close, and that by the time I get above 100, right, I have to hit 7 somewhere above 100. Right? Somewhere between 100 and 150, maybe close to 125. And I want to consider what is 2 to the 7th. Right? So if I'm thinking through my powers of 2, I have 2 to the 1 is 2, 4, 8, 16, 32, 64. 128 is 2 to the 7th. And my value here could very plausibly be 128, 7. So that suggests to me when I plug in 128 for x, I get back 7, which matches graph A. So I'm going to say A goes with A. And that fits my pattern, right? I could logic this out. I gave a lot of structured reasoning for why each one goes in each spot. But once you get, if you're on a test and you get the hang of it, like, oh, this shallower log graph is going to go with the greater base, right? Then you're off to the races, right? You can deduce it right from there. You don't necessarily need to prove it out, but proving it out with specific points on the graph will help you check your work and make sure that your work is reasonable. 18 was another that folks requested pretty frequently. It's a mathier math, right, where we have a function and a graph of the function. And we want to know, right, this particular expression, 150 times 1.35 to the third, right? When does that happen? What year is that true in? Right? So I'm going to start with what we know from exponentials and find, given these 2 points, right, point, other point, an equation that fits this curve. Right? And then I can use what I'm given to figure out exactly what year that's going to happen in. Right? Okay, so I'm going to say that cost per decade, or each decade, will equal my starting value, 150. I can see that from this point, times, right? I have another y value, so I'm going to take the quotient, right? I'm going to divide my y values, and I'm always going to use my rightmost value in my numerator because I'm always moving from left to right. 202.50 over 150. And then over how many decades, right, is that happening? It's over half a decade because that's my 0.5 in my x term, and my whole x-axis is in decades since 1978. So if I have half a decade, I'm going to cover 2 of those to create a decade. So my exponent will be 2 times decades. Right? And in general, if I have to do my multiplication of this factor more times in order to cover a whole decade, then this exponent should get bigger. And if I have to do it less times, it should get smaller. So for instance, if I had like this point, then I would be using d over 2 in my exponent, but I don't. I have 0.5 and not 2. So I have my function, right? And I can simplify this a little bit. In fact, I can do that division, 202.50 over 150, and I, wonder of wonders, get 1.35. So that's exciting because that's my 1.35, from my original, like what I'm seeking, right? And I have that 150 from what I'm seeking, right? So in order for these two expressions to be equal, right, in order for 150 times 1.35 to the third to be equal to 150 times 1.35 to the 2d, those exponents got to be the same, right? So I know for sure that 3 is equal to 2d. No way around it. And that's easy, right? Divide both sides by 2. 1.5 equals d. So it's 1.5 decades after 1978, or 15 years after 1978. And 15 years after 1978 is 1993, baby. All right. Moving ahead. Given another function. I'm going to highlight it so it's easy to keep track of. It's an area in square centimeters of a wall covered by mold. Guys, this just keeps getting grosser. Okay, we can do it. Get through this. Get some mold killer. Get rid of this situation. It's a function of time in weeks since the area was measured. And we're going to explain or show how that we can approximate that area after 8 weeks by multiplying a of 7 by 1.01. So I'm going to warn you, my friends, we are going to use my favorite exponent rule here, right? Which is that x to the a times x to the b equals x to the a plus b. And we're going to do it my favorite way ever, which is backwards. I can just sense it. I see that it's coming. So I know that we have talked about this in this sort of a situation in class, but this is probably some of the trickiest problems that we encounter. So we're going to do one more together. I know that a of 8, which is what we care about, 8 weeks, is equal to 180 times e to the 0.01 times 8. Just plug it into my function. And I'm going to leave that separate. I'm not going to write that as 0.08 for now. And here's why. I'm going to rewrite this function instead as 180 times e to the 0.01 times 7 plus 1. Because 8 and 7 plus 1 are the same. And that's my little tricky trick, right? Where I know I have something about 8, I know something about 8, but I want something about 7. So I'm going to write 8 with a 7 in it, right? I'm going to use a fact about math that I have to rewrite 8 in a way that's probably more convenient to me. And this kind of a path where we like rewrite 8 as 7 plus 1, it feels like a trick. And it's a trick, right? Because it's hard to see that you should do it, but it's a kind of trick that shows up again and again and again as we look at these sorts of patterns. So it stops being a kind of a trick and starts being a way that mathematicians do proofs. And you will see this kind of a use of a rule in a kind of backwards way show up more and more and more as mathematicians prove more complicated cases and more complicated rules. So it's coming back, sorry to say. Now I'm going to distribute. Right? So I'm going to say this is still 180 times e to the 0.07, right, plus 0.01. I'm going to keep them separate. I'm not putting them together because then I get right back there and I don't want to get there. Keeping them separate. Right? And here's my cool other trick. I'm going to start over here and I'm going to consider it in a different color to make it easier to see. What is a of 7? Well, that's going to be 180 times e to the 0.01 times 7, and this time I am going to multiply it out. That is 180 times e to the 0.07. Ah! Oh my gosh, look. It's there, and it's here. Same thing. So when I know that something is equal to something else, I can rewrite it as that other thing. So I can say that this 180 times e to the 0.07 is the same as a of 7. And then using my exponent rule backwards, I'm going to do that in a different order. I'm not going to jump quite that far ahead, right? So I know that I found something that is the same as a of 7, and I'm so excited. But I've got this e term that I'm still messing with, right? So I'm going to rewrite that as 180 times e to the 0.07 times e to the 0.01. So that's my use of my exponent rule, my favorite exponent rule backwards. I had e to something plus something else, so I'm writing it as e to the something times e to the something else. And now I'm well positioned to rewrite 180 times e to the 0.07 as a to the 7th. And we keep our times e to the 0.01. And when I take my e to the 0.01, my calculator, give me, let's see if I can get ABC, E, nope. To the 0.01, 1.01. And we know e to the 0.01 is about equal to 1.01. So I've shown, I opted for show, with a deduction, right, that when we take a of 7 and multiply by 1.01, we get a of 8. I can just, for completeness, write this as a of 8 equals, that's my proof. Whew, that was intense. This is heavy. I think this one will be a little better. And we're in our home stretch. Last several problems. Number 20. Here I'm going to solve them without using a calculator, and good news, I'm not going to need a calculator. When it gets to something that's ugly, I'm going to leave it in log notation. I'm not going to jump to a calculator to see what exactly it is, and that's going to feel so great. It's going to feel so great, right? Leave it. And the way I'm going to approach this is I am going to rewrite each one in a way that makes sense, either by using log notation or exponential notation or whatever is easiest. Here, right, I can use the rule that 10 to some power would have to equal 10 to the same power, right? If I have 10 to a power and 10 to another power, those two powers have to be the same. So I know that n minus 3 has to be 1, right? As 10 is 10 to the first power. Add 2 to both sides, add 3 to both sides, n has to be 4. Done and dusted. Okay. And then I can also solve b by taking my algebra steps. I first want to multiply both sides by 2, right? I can say that 10 to the x then has to be equal to 0.1, right? Which means x has to equal -1 because 0.1 is the same as 1 over 10. Done and done. Okay, similar game. I'm going to this time rewrite 100 as 10 to a power because I have 10 to a power on my other side, and it seems harder to get 100 as my base when I have stuff going on in my exponent. So I can say that 10 to the 1/3 t equals 10 squared, as 100 is 10 squared. And I know those powers have to be the same, so 1/3 t has to equal 2. Multiply both sides by 3 to get rid of that coefficient, and t has to equal 6. 3 down, 1 to go. This one's worse because I can't just easily rewrite 48 as 10 to some power. So I'm not gonna. I'm gonna use logs instead. Okay, I'm gonna rewrite this expression as a logarithmic expression. So I'm going to say the log of 48, so what I take 10 to get 48 is 2x. And then I'm going to divide both sides by 2 and get x equals log of 48 over 2. That's it. I'm done. I'm stopping. Because after this, I would have to go to a calculator, right? I can't divide 48 by 2. That's not how that works. That 48 is inside my log function, not multiplied by. So without a calculator, that's as far as I get, and I am happy to leave it that way. It is precise, it is elegant. It will never be as precise or elegant as it is right now. Everything else will be just a pale estimation, a rounding error. So we just have this. All right, I see technology required on 21, which means they're sending me back to a calculator, which I hate. But it's okay. It's okay. With you with me, I think we will get there. All right. We're comparing the population of Mali to the population of Saudi Arabia. In both models, T represents years since 2014, and in both models, the populations are measured in millions. Well, for this first part, I don't need a calculator, so I'm happy about that. I want to compare the higher population in 2014, and 2014 is my starting year. So I can compare my starting values, and I can see that Saudi Arabia has a population of 31 million in 2014, whereas which is greater than Molly's 17 million in 2014, right? And then I know because the A value, that starting value in each equation gives the population in 2014 based on T represents years since 2014. So another way that I can sort of explain that, if I plugged in 0, right, 0 years since 2014, then these would each be e to the 0 or 1, and I would be left with just 17 million and just 31 million. Then I want to think about which country has a higher growth rate. Well, we can read that directly from the expression as well. Right? No calculator needed. So I'm loving this problem so far. I haven't gone to a calculator. I haven't had to do anything like that. I can just read it right off the equation. My favorite. So in our PERT equations, which these are because they've got a base of e, my rate can be read from the exponent. It's the value that I'm multiplying by the time. So Saudi Arabia, right, has a growth rate of, it looks like 3%, right? And Mali, oh, no, sorry, Mali has a growth rate of 3%, and Saudi Arabia has a growth rate of 1.5%. So I'm going to say Mali has a growth rate of 3% higher than Saudi Arabia's 1.5%. And we know that because the R value in each function gives the growth rate. So that's how I would explain it. So now it wants me to graph them. Right. So we can graph them, right? It's just straightforwardly typing these functions into our graphing calculator. And what we're gonna see, right, is that they will intersect because of stuff we talked about a little earlier, right? Saudi Arabia, which I was doing in blue, started with a population of 31 million, but then grew slower at like 1.5 rate. So just going to do something like that. Whereas Mali starts with fewer people, but grows faster. So it may not look exactly like that, but it'll look something like that. And we can pop over to Desmos and just see what they would look like. Okay. I am gonna do a whole new thing. And I'm not going to lose this function because I want it for tomorrow. Give me a new graph. All right. So I have M of, and we're going to do X because it's Desmos, equals 17 times E to the 0.03 X. Whew, there it goes. And we're going to have S. And again, because we are in Desmos, we are going to do of X equals 31 times E to the 0.015 X. Oh, because I want 0.03. Pardon. Well, I fixed my function. Whew. Okay. Oh, I see them. Okay, so I can zoom out. I can zoom out. I can zoom out. Look, it does what I said they would do. It crosses, right? One starts lower, right? Mali starts lower and gets higher, and Saudi Arabia starts a little higher, but grows more slowly. So I can just tap this little intersection point here, right? And it looks like it intersects at about x equals 40 years at a population of about 56 million. So 40 years, 56 million, give or take. So yes, at about 40, 56. So in 2054, right, so 40 years after 2014, which is our starting year, both will have about 56 million people. Holy cow. Final stretch, final stretch. Keeping it real. So conveniently, they have graphed for us this function g that contains the point -2, 1 and the point 164. So we have both of those and the general shape of our curve. We want to write an equation, g of x, to represent this function. And good news, this is our like 2-point problem, right, where we use the values that we have, even though we don't have initial starting value. We solve for a, and then we have a function. So our first step, right, is to say that, okay, g of x is going to be a times what's my b, right? And so I always move, right, uh, with my right-hand side divided by my left-hand side because I'm always moving from left to right. So I want to know what I have to multiply my left-hand side by to get my right-hand side. So my b is going to be 1 over 64 over 1. That's good news. Love dividing by 1. And we're taking that to some power, I don't know what yet, right? And then I want to think about, right, for my power, before I just commit to this x, right, how far I go, right, how many x units I cover to get there. So that's when I move from -2 to 1. So that's a distance of 3 units. So I want my model to measure over 1 unit. So I'm going to take that to the x over 3 power. I divide by 3 in my exponent because I want to shrink, right, the area that I'm considering. Okay, I have a function. I need to solve for my a, so I can use either of my points to solve for a. And I'm going to use 1 over 64, and that may sound crazy, but trust me, it's all positive numbers. I already have a 1 over 64 kicking around in my function, right? Because when I divide by 1, it goes away. So I can say my y value, 1 over 64, is equal to a times 1 over 64, my b value, to the x over 3 power. And here my x is 1, so it's to the 1/3. Okay. So I want to then see what this guy is. What's 1 over 64 to the 1/3 power? Or what is my cube root of 1 over 64? Well, I know that that's the same as the cube root, sorry, the cube root of 1 over the cube root of 64, if I'm remembering my radical rules. And I know that that is the same as 1 And the cube root of 64 is 4. So I feel great about that. So I then know that 1 over 64 is equal to a times 1/4. I can multiply both sides by 4. 4 over 64 is a. So a is 1/16. And then I can write my function. So I can say g of x is equal to 1/16 times 1 over 64 to the x over 3. It's not lovely to look at, but doing the math for it was not that bad. And when I started looking at this, I had some negative numbers, I had fractions. I was really concerned that my math was going to get super, super ugly. Notes to take away from this problem: stay in fractions. As long as you possibly can, stay in a fraction. Stay in an ugly fraction, right? Stay in a messy fraction. Don't go right to decimals, because decimals will make it harder to use the rules that you have and harder to see what you're working with than fractions. And you just have to like write a lot more numbers, which I hate, and maybe you hate too. Making progress, making progress. 23. We know that 2 to the 10 is 1024. This kid is going to estimate Tyler. Maybe it's Mr. Beeks, maybe it's not. 2 to the 20th at about 1,000,000. And that log base 2, oh, we better get there. Almost there, 5 more. And that log base 2 of 1,000,000 is about 20. Do we agree? Right. Well, let's find out. I want to consider how I can relate 2 to the 10th to 2 to the 20th. Right. And I'm going to do one of those annoying things that I keep doing, where I use my exponent rules. I know from my exponent rules that 2 to the 10th times 2 to the 10th is 2 to the 20th. Because when I multiply two things with the same base, I add the exponents. Okay. So then I can say that 1024 times 1024 is 2 to the 20th. And then how does 1024 times 1024 compare to 1,000,000? Well, it's going to be more than 1,000 times 1,000, which is 1 with 6 zeros, 1,000,000. Right? So 2 to the 20, aka, oh, yeah, 2 to the 20 is a bit more than a cool million, right? And if I write that in log form, right, then that's my log base 2 of 1,000,000 is kind of close to 20. So it's an okay estimate. It's a pretty good estimate, but not a perfect estimate, right? So we can say, okay, job, Tyler. Oh. 24. Dude, we are so close. So close. And look at this. Just write them in exponential form. And we know that ln is the log with a base of e. So this is going to be pretty straightforward because these are all ln's, so we're writing them as e to some power, right? So ln of 618, e to the p is 618. Ln of q equals 2, e squared equals q. Huh, I love this problem. Ln of 100 equals t, e of t equals 100. Right? Ooh, and now this one's funky. So ln of e cubed is 3, right? Then e from my base cubed from this 3 equals what's in my parentheses, e cubed. Whew, easy peasy. Moving on. The function f is given by another PERT model. So lots of these were PERT equations, folks. And I know a bunch of you had questions about how to deal with PERT equations specifically. 25 is a fantastic example of that, but any of these functions with e in them are PERT equations. Here it's given us a balance in a bank account in thousands of dollars. So again, messing with our scale, 2 years after it was open. Okay. Opening balance, we're going to look to our initial value. Right from our function, it's 10, but we are in thousands, so $10,000 will be our starting balance. Okay. And we want to know when it reaches $1 million. I just really want to know what happens at 1 million. Right? Now my function works in thousands, so I have to write 1 million as a number of thousands. And 1 million is indeed 1,000 thousands. You can just divide by 1,000 to get there. So I'm going to say I want to know when my function is equal to 1,000. And my function is 10 times e to the 0.07. That's a 7% growth rate, which is not too shabby for an account, to the t. Divide both sides by 10, because I'm solving for that t. And I can see I have 100 equals e to the 0.07t. Now I'm going to use my natural log because my natural log is my log with a base of e. And so I will say ln of 100 equals 0.07t. Divide both sides by 0.07 and plug it into a calculator. And I get t equals 65.788, etc. years. Not too bad. Okay, so even at that pretty generous 7% growth rate, it's going to take us a whole long time if I don't add any other separate deposits to my account to get to $1 million. 26, another nice PERT equation with an e term there, right? Whew, but I'm asked to do something really quite subtle with it, right? I'm asked to find a function where that is going to intersect with this function, right? So I need something that either starts higher but grows slower, or starts lower but grows faster. And I am arbitrarily going to pick a g of x that starts higher and grows slower. So for starting higher, I just need some value for a starting value that's greater than 20. I'm picking 100, but you could pick 22. You could pick 21.5. You could pick 1 million. Anything higher than 20 will do. Right? And then I need something that's going to grow faster than e to the x. Well, one thing that'll grow faster than e to the x is e to the 2x. That's for sure. It's definitely steeper. It's 2x is bigger than x, right? For, again, we are considering positive values of x here. Oh, this wants it to meet. I'm going to back us up, and I'm going to cut that part of this video if I can figure out how. Okay, moving on to number 26. I have a nice neat PERT function, right, with my e term. And I need to find a function that intersects this graph. So I need either something that starts lower and grows faster, or something that starts higher and grows slower. And just arbitrarily, I am going to pick something that starts lower and grows faster, but you can do it the other way. It's no big deal. So g of x, I need a starting value that is less than 20. I'm going to pick 10, but you could pick 5 or 2 or 1, right? Anything that's less than 20. And then I need something that grows faster than e to the x. So I'm going to pick e to the 2x. Because I know that that 2x for my positive values of x is always going to be greater than x. And so this function will grow faster, right? Starts lower, grows faster. Now I want to take a look at something that doesn't intersect, right? So we can call that h of x for this question. And in this case, I need either something that starts higher and goes faster, right? Or something that starts slower and grows slower, right? So something that's either going to race way ahead of this function or never keep up. And I'm going to pick something that starts higher and grows faster because I can. So I need, for my starting value, anything higher than 20. So I'm going to pick 100 arbitrarily. Right? And then I need something that grows faster than e to the x. So I'm going to pick e to the 2x again, because I already figured that part out. So this is going to start higher on my graph, and it's going to be steeper. I could even have picked like e to the x, because it would sort of be parallel in a way, right? They would start at different points, but they would grow at the same rate. So our initial function would never be able to catch up. But either way, those functions will not intersect. I cannot believe we have more mold. Okay, we're so close. I think completing the table is boring because we are growing exponentially and doubling every month, and it's relatively straightforward to get them in. So after 1 month, I'm doubled. After 4 months, I have 16 times as many. 32 is an actual power of 2, so that's my 5, right? Doubled again. 64 is my 6, doubled again. And my others are a little harder to see because they're not powers of 2. But I know that my area in square feet, right, my exponential function is going to do something like 2. Did my pen die? My pen died. All right, folks, for 27 and 28, you're just going to have to tune into class or come into office hours. I have no more pen. The battery on the iPad's supposed to die. We made the review packet too long. We can talk about this one in class. We can talk about the next one in class, but I'm going to call it here for tonight. Thank you for your kind attention, and I will see you soon.